weekly colloquium, both those of you in the room and those of you virtually. So during the talk, we'll have questions from in the room. If you're on Zoom, please type questions into chat. And after the talk, you could raise your hand or type questions into the chat. So today's speaker is Roman Lutchyn. He got his PhD at the University of Minnesota, was subsequently a postdoc at the Joint Quantum Institute at the University of Maryland and NIST, and is now at Microsoft Quantum Station Q. His title today is Topological Quantum Computation with Majorana Zero Modes.
Thank you, Dan, for the introduction and for inviting me to speak at the Aspen Center for Physics. So this is the title of my talk, and here is the outline. Just for the sake of bringing everyone on the same page, I want to start with the introduction, general introduction to topological quantum computing, and discuss what's the basic idea. Then I'll focus on practical realization of topological quantum computing in semiconductor, superconductor heterostructures. And finally, I present some scalable design blueprints for a topological qubit based on this idea. Okay, so right, so we already know, even right now, that quantum mechanics plays a role in our everyday life. You know, one of the examples is MRI, which is based on quantum mechanical object, nuclear spin. There's also lasers, transistors, and many other devices. But if we were to classify these devices, we could say that there are some elements of quantum mechanics that play a role, but these devices or these technologies do not take full advantage of the power of quantum mechanics. And two basic principles that I wanted to highlight that are important for quantum mechanics is principle of quantum superposition, quantum entanglement. And quantum mechanics, basically, because of these two principles, has an advantage over say, classical computing in the sense that it allows to explore different paths at the same time. So there is this massive parallelism built in computations when we use quantum mechanics. And so that's the basic idea behind, quantum computers that, which I defined here on the slides, that quantum computer is a new type of quantum machine that exploits quantum properties of information and could perform certain types of calculations far more efficiently than classical computer. So it is interesting, for somebody like me working on hardware realizations to see how industry or how others perceive quantum computation and as a technology, future technology. So several quotes that I wanted to show you here from actually business people, people who are not in the field, but this is what they're thinking, which is actually encouraging. And I agree with this point that we need to understand how to leverage quantum mechanics for our practical applications. So here's another slide which shows what different areas in industry are actually thinking and using small quantum computing machines to basically for their purposes. And you can see that by far finance is leading ahead. So bottom line is that unlike in the past where we sort of during the transistor era we invented the transistor and then applications came after that. Here there is an interesting paradigm that industry is already thinking what is impact of quantum computing on their respective fields. So there are bottom line is that there are many applications. Let me now move to the hardware aspect. And so one can ask, okay, so how do we build this quantum computer? What is needed to have this quantum machine? So the basic element of a quantum computer, or you may think about equivalent of a transistor, is a qubit, right? A qubit is a controllable quantum two-level system. So the keyword here is controllable and quantum. So in a sense, we want to make sure that we can create arbitrary superpositions on demand. And so that's the idea for the qubit. And right now we have different approaches playing in parallel. So some people are building their qubits based on some microscopic degrees of freedom. So iron qubits, some diamond-based qubits, silicon qubits, and others. And there is a second class where one is relying on some kind of collective degrees of freedom, such as say superconductor, where it's a phase and order parameter that are playing an important role, but they actually encompass the dynamics of billions of electrons. And then there is another extreme, which is basically topological qubits, where we try to delocalize this information, as I will explain more in this talk, so that local noise, local errors do not disrupt and do not read this information. So one can ask, what is the main challenge? So we have these systems, physicists and engineers have been working in this field for quite some time. So what is the main challenge? And the main challenge is that we're trying to control quantum system. And so we need to couple to that quantum system. But during this, or during the measurement, or during even evolution, the system is coupled to some parasitic degrees of freedom, some unwanted degrees of freedom. And so the environment basically induces errors. Essentially the game is to isolate these degrees of freedom and make sure that the control degrees of freedom are strongly coupled to our qubits so that we can quickly do our gate operations, but all the other degrees of freedom are decoupled. So that's the main game here. So so this process is called quantum decoherence. It induces errors. And if we had a classical system, classical systems also have errors. There is a simple solution. If you take a CD, there are many layers where we just introduce redundancy. We create many copies, and so if there is error in one copy, you can just read it off from the other place where you stored information. But this is not possible in quantum mechanics. And in quantum mechanics, the situation is more complicated due to no-cloning theorem. And the second aspect is the measurement collapses the quantum state. So we cannot really stop our operations and check whether we have an error or not, because by doing so, we will collapse the state. So there is, however, a solution, and solution is to create redundancy and encode a logical qubit in many physical qubits, and then use some special measurements which can identify source of error without collapsing the information that we care about. And so the basic idea was introduced by Shor in 1995, and there are several error correcting code known to us by now. So, however, this approach, which I call active error correction, comes as a price because we have to add large overhead, and there is a threshold for these errors for the individual qubits that we need to overcome in order for this approach to work when we scale up. And typically, this threshold is 10 to the -4, and this number is specific for the type of system that one is working with. So this is the basic idea of, I would say, conventional quantum computing approach. or quantum computing approach, which is based on active error correction. So there is another idea, and actually this idea was introduced by Alexei Kitaev, who's here in the audience. And this idea is based on topological, this idea is based on the following. So if you have topological degrees of freedom, topological phase of matter, and topological phases of matter, they have very non-local degrees of freedom. So if you have such a phase, then such a phase would be, or the information encoded in these non-local degrees of freedom would be insensitive to local perturbations. So and most of our sources of errors are local, and therefore by using clever encoding information in these degrees of freedom, we can implement hardware-based error correction. So that was the basic idea. And let me discuss now a little bit more about topological phases of matter and how, where do we find them in real world. So first of all, there is a joke among topologists that the donut and the coffee cup are the same because they can be deform into each other using smooth changes or smooth deformations. So here's an example that donut and the coffee cups, they have one hole and therefore they are topologically equivalent. And if you take a donut and just bite it a little bit from the outside, but do not destroy it, do not cut through the donut or something like that, use some small changes to the geometry, the information encoded in the fact that you have one hole in the system will be preserved. And so that's roughly the idea, except topology in kind of condensed matter systems is encoded in some kind of abstract space. So topological quantum computing depends on two facts. First, we need to find a topological phase, and not just topological, but non-abelian topological phase. It's a special phase of matter, which I'm going to explain. So this phase of matter is characterized by the energy gap. So as you can see, let me make sure my pointer is visible. As you can see here, there is actually degenerate manifold of ground states. There is a gap and there is a excitation spectrum. So in topological phases of matter, they emerge as a low energy description in certain situations, and when they do, they are characterized by finite correlation lengths, which is related to the gap. And in this sort of topological, in this effective low energy field theory, the correlation functions are described by universal numbers that are characterized by certain rules that correspond to topological field theory. And also the characteristic feature is topological ground state degeneracy. That is, the ground state degeneracy depends on the manifold in which the system lives. And so then another prerequisite for topological quantum computing is the appearance of these special excitations. These are non-abelian anyons, and it depends on our ability of manipulating these non-abelian anyons. So, that is the basic idea, and that's a definition of the special non-abelian topological phase that we want to find in real world. So I mentioned word anyon, and I want to just bring everyone to the same page and introduce this concept of anyons. And it has to do with statistics, quantum statistics. So in 3 dimensions, we have bosons and fermions. And this fact is related to triviality, essentially, of double exchange. If you take two particles and exchange them together, then it's equivalent to basically moving one particle around another. And if you have third dimension, one can shrink this operation to essentially a point, and therefore, t squared is equal to 1. And there are two roots of this equation, plus minus 1. But it was pointed out in late 70s by Lenas and Mehren, and then later by Lutchyn, that in 2 dimensions situation is special, and actually you don't have this degree of freedom outside of the plane. So therefore, clockwise and counterclockwise exchanges can be different. And later, we also realized that there are 2 types of anyons. One is called abelian enyon, and this enyon under exchange introduces a phase, and this phase can be different from 0 to pi. So it's in here it's called theta. And non-abelian anyons are the anyons where the exchange leads to a non-trivial transformation in the manifold of the general ground states. So it actually acts as a matrix. Here, if you have exchange of x1 and x2, would generate, say, matrix M. And if you have exchange x2 and x3, would generate matrix N. In general, matrices do not commute, and hence, and therefore, if you have a dense set of these matrices, one can think about implementing gates using these matrices and essentially perform certain quantum computation. So the idea is, if you have this degenerate ground state, and if you have this transformation, which are described by matrices, then we can encode our information in this ground state. So we never use excited states in this approach, unlike in conventional quantum computation. And so, in a sense, ground states don't decay. So this way of encoding information is advantageous. Okay. So far I've covered more abstract part of the introduction, but now I want to show that these topological phases of matter, possible to realize experimentally in the laboratory, and in fact we know some of them. Say for example, integer quantum Hall effect, where the resistance is quantized to the precision that is unprecedented, and this precision is preserved even though samples are different, they have different realization of disorder, and so on and so forth. So that's an example of topological phase where the quantity, specific quantity Hall resistivity is quantized. This is not non-abelian phase, and non-abelian phases are proposed realization of non-abelian phases goes back to also fractional quantum Hall effect. So there are special fractions in fractional quantum Hall effect. These are called, say, 5/2 even denominator fractions, in which the ground state of the system has these special excitations, and people have demonstrated that they have non-abelian character. I think one of the main historical, powerful connection that really gave boost to this field was the paper by Reed and Green that established a correspondence between fractional quantum Hall states, which generally are strongly interacting and very difficult to understand even numerically and experimentally, to a system that is weakly interacting and more amenable to, say, approximate mean field type description. So this connection between Murid-Pfaffian fractional quantum Hall state to the wave function of chiral P-wave superconductor pointed out that even weakly interacting theories can have these degenerate ground states. And so here's an example. If we introduce a vortex in this chiral P-wave superconductor, it turns out that this vortex has a special mode, and this mode is called Majorana zero energy mode. And this mode satisfies, the operator corresponding to this mode satisfies these relations. So it's a self-conjugate operator. It squares to 1, and different gammas anticommute with each other. So this is interesting because the fact that this mode is at zero energy tells us that if we have several vortices, then we can start to introduce this ground state degeneracy. So let's look at this example. These red, the red sort of circles and dark representative vortices in Majorana states that are bound to them. And so if you look at the system and we have many of these vortices with these Majorana zero energy states bound to them, then we have large ground state degeneracy. And this ground state degeneracy can be seen if we start artificially introducing, say, Dirac fermions out of 2 Majorana fermions. So let's in our head perform the following pairing. So we will perform the following construction. Out of these 2 Majoranas, we will form fermion A, and out of these 2 Majoranas, we form fermion B. Then immediately you can see that if you have 4 Majoranas, you have 4 degenerate states because they're all at zero energy, and occupation by even and odd fermion does not introduce any energy cost. And we can enumerate Hilbert space, and here are the 4 degenerate states. And these degenerate states, they can form a basis of a qubit, actually. And that was the idea of Alexei Kitaev, that from 2n Majoranas, you can construct n-1 qubits. This n-1 appears because we want to have fixed fermion parity in the whole system. And so if I do that, then I'll have to discard these 2 states. So so far that's a simple model which shows how to generate this ground state degeneracy. And I want to emphasize that because these Majoranas are far away from each other, so these vortices are far away from each other, much larger than the correlation length that I introduced before, they are locally indistinguishable, meaning that there's no local operator that distinguishes between occupation, even an odd occupation, in the encoded fermion parity in these 2 modes. Then what is interesting that one can do with these sort of Majoranas, which essentially represent, colloquially speaking, a half of an electron, you can exchange them together, and you can move these vortices and exchange them together. And when you do that, it turns out that one can show, as pointed in these papers, that this is exactly the transformation that I described abstractly before, which basically changes the initial state and creates a superposition of states 0A, 0B, and 1A and 1B. And finally, let me show you that we don't really need 2 dimensions. In quasi one-dimensional networks, we can also do similar transformations. One just have to do these transformations cleverly, just move these Majoranas around in a way like you're parking cars in parking lot, and it also works. So 2-dimensionality is not strictly needed in lower dimensions. 1 plus epsilon could also work. Okay, so any questions so far from the audience? Maybe somebody on the, okay.
So what, in these kinds of sort of designs, How rapid can one expect gate operation?
I'll
You're trying to be idiotic, and I'm
Yeah.
just worried that this is exactly the opposite of what your big finance
right,
company is going to like.
right. I'll get to that at the end of the talk.
Could you please repeat the question for those on Zoom?
Yes, sure. So the question was, in this approach where we actually move, quasi-particles around, was what is the limitation on speed? How quickly we can move these excitations around, and what implication this kind of limitation has for any practical quantum computation. That was the question. And, I will address this question at the end of the talk. It is not a very practical approach, I have to say, and we have a better idea. Okay, so now let me move to more practical realizations of Majoranas, and let me show you how one can realize them in the laboratory. So as I described, there are two classes of sort of proposals. So one is based on some intrinsic interactions in the system. So one has to be lucky to have material with the right type of interactions. But the other approach I think is more promising, because we've distilled, we've distilled our findings to necessary ingredients to sort of more engineering-like approach. So we understand that we want to realize this spinless p-wave superconductivity. And so if we combine the properties of different materials, perhaps we can do that by cleverly constructing these boundary Hamiltonians. And this is essentially the breakthrough idea from Fu and Kane, that they showed that similar Majorana zero energy states can be realized at the interface between topological insulators and Aspen superconductors. So this is very appealing because these systems are much simpler, and we understand them much better, and we understand exactly what ingredients we need to include. So a couple of years later, there was a number of ideas how to realize similar physics using just conventional semiconductor, S-wave superconductor, and using various ways of breaking time reversal symmetry. And I want to focus on that approach because I think this approach is very promising, and because it relies on ingredients that we well understand. So the essence of this approach is that we take a quasi one-dimensional wire, contact it with an S-wave superconductor, and in simple realization, one can just simply apply magnetic field along the direction of the wire. So this wire, there are semiconductors where there is a large spin orbit coupling appearing due to the inversion symmetry breaking at the interface. And this inversion symmetry breaking couples spin and orbital motion. And that's one of the key ingredients, because we want to remove one of the spin degrees of freedom in order to make spinless superconductor, right? So, so if we use this spin orbit effect and together with the Zeeman effect due to the applied magnetic field, and notice that in this case, sigma y and sigma x do not commute with each other, we end up with this simple band structure where spin orbit basically gives the shift to the sides from zero momentum, and this Zeeman interaction opens a gap in the spectrum. What is interesting here is that when the chemical potential is exactly in the middle, you have a spinless system, but the actual spin is not conserved. It actually gets locked with orbital motion. So there is a projection of the spin up and down on the opposite sides of this band structure. And what is interesting, so the fact that we have up and down projections are important because such system cannot be coupled and proximitized by an S-wave superconductor. So if I now concentrate on this S-wave pairing term and rewrite it in the basis of these states, and then eventually project to the lowest, to this lowest occupied subband, what one find out that fermion anti-commutation essentially annihilates these two terms, and only one term survives, and one can show that. Sorry, I said something wrong. So I'm projecting, and I'm throwing away these psi pluses because they are unoccupied here. So this is the state corresponds to its excited state. So I'm left with the psi minus, and because of fermion anti-commutation relation, we this delta p has to be odd on the momentum, and so the lowest order expansion gives you a p wave, basically pairing potential. Notice that this was a spinless system. There is just one pair of kf Fermi points, and therefore we essentially realized a spinless p-wave superconductor that Alexei actually wrote about 10 years before. And so we know that this spinless p-wave superconductor will have zero energy states at the opposite ends of the wire. So what is needed to realize this proposal is to have a semiconductor with large spin orbit interaction, large G factors, so that we open Zeeman gap, and we form good contacts with metals so that we have a large proximity effect. So essentially, this is the basic idea of the proposal that was put forward by the Maryland team and also the team from Weizmann, Bayou-Al-Oreg, Gil Rafael from Caltech, and Felix von Oppen from Freie University of Berlin. And this proposal is interesting because it's very simple. It's one of the simplest way we can realize topological superconductivity in quasi one-dimensional systems. So here's the phase diagram for this system. As I said, we have to exceed some critical value of the Zeeman of magnetic field in order to open a gap in the spectrum. So here we have a trivial phase, which is connected to sort of S-wave superconductor, and here we have a topological phase. And at the transition between these two phases, we have a topological quantum phase transition where a gap is closing. So this system is easy to simulate on a computer, and one can easily plot density of states as the function of length of the wire and energy, and indeed define these two different phases. So this was trivial phase, just nothing below the gap, and this is topological phase where we have these Majorana zero energy states at the opposite ends of the wire. So that's the basic idea. So now, soon after this proposal, there were experimental attempts to realize this system. And the first paper that attempted to do that, the first group that attempted to do that was a group in Delft, led by Leo Kuhn-Hohen. And here's the data that was obtained by the group, and here's basically results of some previous simulations. So the simplest thing one can test in order to test this theory is to see that upon application of certain magnetic field, we have zero energy states in local tunneling conductance. So indeed, when they exceed some critical field, there is a zero energy state appearing in tunneling conductance, which is consistent with the Majorana scenario. But what was immediately obvious in these measurements is that we have to work and improve this material system. So rather than having BCS type density of states, we see that there is a soft gap even at zero magnetic field, meaning that there's this V-shaped subgap density of states. And this indicates on the presence of disorder. So disorder is, competes with topological P-wave superconductivity, and after some critical value can even destroy. And so one has to improve the material system and make sure that we satisfy certain requirements, which I'm not going to go into, but it is clear that disorder is an issue here. So these initial papers, they actually inspired a lot of experimental activity, both in measurements and kind of detecting, but also in material science. So material scientists try to take it seriously that the interface needs to be improved, and they come up with different ways how to clean and how to make these interfaces epitaxial. And so this is one of the early papers by Peter Krogstrup, who showed that actually indium arsenide, wire, and aluminum has a very good interface, and if you grow it epitaxially, that density of states looks like BCS and it looks very clean. So later on, similar improvement was done for indium antimonide and aluminum system. And indeed, if you look at the cut between sort of epitaxial way of growing these interfaces and evaporated, then we see clearly that epitaxial is much better than the evaporated method of depositing superconductor. So this was the key material science improvement needed for the field to actually improve the signal, improve the signature. So now I'm getting into the topic of the origin of zero bias peaks, which is controversial because it's still debated in the field. And the problem is that we cannot really, the problem is that zero bias peak is necessary, but not sufficient condition for detection of Majorans. In simulations, we can look and see what exactly happens. We can plot different parameters, but in experiments, it's difficult to know this. So we rely on some secondary sort of effects, secondary properties in order to interpret experimental data. And there is a long debate in the community whether zero bias peaks, they correspond to real Majoranas, or maybe they correspond to some kind of disorder-induced zero energy states, or they correspond to some kind of accidental Andreev states. And so rather than dwelling on this topic and kind of discussing zoology of these zero energy or zero bias peaks, I actually want to propose an alternative solution, which I think will help to resolve these issues. And the idea is that we want to try to detect topological phase. Okay, so topological phase, it should be stable to small changes, local changes in the left or right junction. So that's one. And second, we should be able to see this topological phase transition and correlate the appearance of zero energy states at the opposite ends of the wire with the closing of the gap and reopening. Okay, and it turns out that there is a simple device that will allow to do that. This device we call a 3-terminal device, and this device allows to measure local conductance where current from this lead essentially flows into superconductor and superconductor is grounded. Similarly, from the opposite end, there's a similar process, and they correspond to the diagonal terms in this conductance matrix. But there's also a process where current can flow from this lead to another lead. And this current should be enhanced if gap is closing, induced gap is closing, because in this case, correlation length is divergent. So here is the example of the simulations where we plot local conductance and non-local conductance. And one can see that there is a zero bias peak at this point at field around 0.5 Tesla or so. But if I look at the local conductance, there's nothing happening here. So this is indication that the zero bias peak that we see in this case in simulation appears due to this fine-tuned state in the junction. However, after the closing of the gap, which happens around 1 Tesla, we see that there is indeed zero bias peak that appears. There is reopening of the gap, and there is zero bias peak that appears. And this is the peak that corresponds to true Majorana, corresponds to closing and reopening of the gap and appearance of the zero energy states at the opposite ends of the wire. And so this experiment, we believe, is the key experiment to kind of resolve this issue whether we see quasi-Majoranas, Andreev state, or disorder physics in our real devices. And in fact, we recently put forward a protocol to identify a topological phase. And this protocol essentially encompasses these basic ideas that we need to correlate the appearance of zero energy states or zero bias peaks at the opposite ends of the wires simultaneously with closing of the gap in non-local measurements. And if you do that, we want to map out a phase diagram that looks like this, where these different data points here are connected to each other, so statistically connected to each other. And most importantly, this protocol, once you determine the algorithm and you determine coefficients, how to analyze the data and sort of put thresholds where we say, okay, this is above the threshold, this is the signal below the threshold, it eliminates basically human bias and is once you've established these parameters and gives you an answer, yes or no answer, whether you detected the phase and in what parameter space this phase exists. So that's our proposal to the community, that combination of these different measurements that probe the gap and correlations is very promising and reduces increases our probability for detection of true topological phase. So that's the idea. And now I want to switch gears and talk about another interesting idea, how to realize topological superconductivity. Here's a question. Okay.
Because you're relying on a clean system to get
Yes.
correlation.
Okay, so there's a question from the audience, and the question was, what would disorder do to this protocol? So we know that topological phases are stable to disorder up to some critical value, right? And the parameter that one should compare is the localization lengths due to the disorder with coherence lengths in the p-wave superconductor. And this disordered correlation lengths, the localization lengths, should be larger than p-wave coherence lengths in order to stay in topological phase. So in this paper, we've explored 3 different possibilities, disorder including, and we show that this protocol basically allows one to distinguish between different possibilities. So I don't have slides here, but we've analyzed disorder, we've analyzed asymmetries between barriers and other realistic effects, and we have shown that this protocol detects correctly false positives. Okay. Yeah, so let me switch gears and talk about flux-induced topological superconductivity in full shell wires. This is a new idea how to realize, again, in similar semiconductor superconductor heterostructure, but the control parameter here is the flux. So very interesting phenomenon was observed by Copenhagen group led by Charlie Marcus, is that if you take a semiconductor wire, and you create this superconducting shell and look at the local density of states in the wire, it behaves very different than the well-known little Parks effect, where we just have a simple cylinder, superconducting cylinder with a hole inside, or insulating core. And the interesting observation is that when we have magnetic field, which corresponds to the integer flux winding around the shell, there is a zero, close to zero energy state appearing in the spectrum, and this state is not present in when we just have S-wave superconductor. And so the question was, what is the origin of this zero energy state? Is it some fine-tuned trivial state, or does it have any topological origin? And so that's where we came in, and we realized actually that this system, which has similar ingredients, has spin-orbit coupling, but rather than Damon field, the dominant effect is the orbital contribution of magnetic field. It still maps to the same semiconductor nanowire Hamiltonian. In certain approximation, if you assume a cylindrical model, so you have a cylindrical thin shell model, then we can show it analytically, but even more powerfully, we can show it in sort of realistic simulations, which take into account hexagonal shape and different details of the geometry, electrostatics of the wire that still holds true. And here I want to show these simulations. So this is the phase diagram. The red regions are topological regions, and the gray regions are non-topological regions. And if we park in this specific point over here, then indeed we find in a finite system that you have these zero energy states at the opposite ends of the wire. Then if you look at density of states, what we find is that at the end of the wire, we have zero energy states in the first lobe, but in the middle of the wire, you don't have anything. So the system is gapped, and indeed, we have these delocalized zero energy states. What is remarkable actually is the resemblance between simulations and an experiment. These simulations, they are not fine-tuned to the experiments. We used some realistic parameters that we know and these parameters have been measured independently. But if you put everything together, then we find that indeed the experimental data looks similar to the Majorana scenario. So of course, this is again in the class of zero energy states. So we want to take the next step forward and show whether we have expected, say, scaling of the energy splitting between zero energy states due to the finite size effects. And in order to do so, experimentalists devised this very clever experiment where they used Coulomb blockaded islands. So these islands are now floating rather than grounded. So when you have a floating island, there's Coulomb energy that one has to pay in order to add extra electron to the system. So if you have just an S-wave superconductor, we know that the ground state in that case is 2e periodic. And so we expect to see changes by 2e. However, when we have spinless p-wave superconductor, ground state degeneracy can accept these one electron. Because of ground state degeneracy, we can accept these single electrons. And so this even odd effect, the difference in even odd effect, almost vanishes up to these small corrections which appear due to the finite energy splitting. And topological scenario predicts that this finite energy splitting should be exponentially small. So by using this full shell wire and by using wires, these Coulomb blockaded islands of different lengths, we can see there's different lengths. One can test this hypothesis and see how this even odd effect disappears as we make system longer and longer. And so here is the data, and you can see signals. The position of these peaks tells us about these small differences between even odd effect. But ultimately, when we put everything together, one finds that this residual difference between even odd effect collapses on this exponential plot, which indicates that we have exponential splitting as a function of system length. So this gives us another independent confirmation that we are dealing with a gap system, and we're dealing with these zero energy states that appear at the opposite ends of the wire. So, so I think these two realizations of very similar physics, pinless p-wave superconductors in quasi one-dimensional systems are very promising. They have their virtues, and one of the nice things about full shell wires is that the wire is never exposed to the sort of outside world. You know, during the growth of the wire is covered by superconductor, and all the charge impurities that can potentially appear in the system, they get screened by that superconductor. So that really helps in terms of satisfying these disorder requirements. So at the end of this talk, I want to switch gears to the last part of my talk, which deals with scalable design for topological quantum computing. So I've introduced on the previous slide a single wire and two Majoranas at the opposite ends. But let's imagine we have mesoscopic island, which has 4 Majoranas in the same end and has a global charging energy. Then this island will have residual ground state degeneracy, which corresponds to these states 0 and 1, where parity of each of the 4 Majoranas can be either a pairwise parity is even or odd. And so this is a degenerate two-level system. Now, physically, one can realize the system either by fragmenting the wire and having topological segment here separated by the trivial segment. So in the case of semiconductor proposal, this can be achieved just by tuning gate voltage underneath to a different location. So in this case, this will be trivial phase, in this case, topological phase. Or another idea is to take 2 wires and connect them together by a trivial superconducting bridge so that they have just overall charging energy. So these two systems, they will have degenerate grounds, it's essentially a degenerate two-level system where we can control these hybridizations, these splitting energies by making devices, by making wires long enough so that these exponentially small splittings do not interfere with our computations. So the idea is to use different scales, correlation scale, coherence length is determined by the gap, superconducting gap, charging energy is determined by the size of the island and the gate's electrostatic environment. And we want to find the regime in which we satisfy these constraints that Majoranas are far enough from each other. So there's very small splitting, exponentially small splitting between them, but at the same time, they have overall charging energy. And then to address Vadim's question, we are not going to be moving these quasi-particles. Rather, we will use measurement-based approach, which is based on anion state teleportation. So it turns out that one can implement our quantum gates rather than just moving these defects around. And in the case of p-wave superconductors, these are massive vortices and classical objects. We don't want to move them because it costs a lot of energy. We want to measure them. And so what is the measurement? The measurement involves quantum dots, which we can couple and decouple from the qubit by just electrostatic control. So here's an example. This is a half of this two-sided tetron, and one can see that by coupling to this quantum dot to this Majorana island, we essentially create a loop where the charge goes like this, and this loop measures fermion parity encoded in these Majoranas, gamma 1 and gamma 2. And so projective measurements of these Majoranas, they essentially allow us to do this anionic state teleportation. We can also create couple 4 Majoranas together by creating a larger loop. So this way we will couple, we will introduce 2 qubit gates. So in this case, these 2 quantum dots are just disconnected from each other, and so the current flows like this, and it also projects the system to this parity of 4 Majorana fermions. So just to illustrate this idea, one can show that in a two-sided hexagon qubit, which now contains 3 wires, so 6 Majoranas, coupled by a trivial bridge, one can implement braiding or exchange, braiding transformation that I talked about at the beginning of this colloquium, just by using 4 different projective measurements of Majorana parity. And these projective measurements are not commuting, and so therefore we are implementing a non-trivial operation. So that's how we want to implement gates, and I'll show you one important gate, which is braiding. And finally, let me lay out the whole architecture, scalable design for this proposal. And so the idea is to tile these Majorana islands and connect them with quantum dots. So you can see this two-sided tetron. Here we can have a quantum dot, which will measure different Majorana parities. And because we have electrostatic control, we can either create these dots or lower the barriers and remove these dots from computation. And by doing this sequences of projective measurements, we can perform topological quantum computation. There is one caveat that I want to emphasize. Of course, there are no miracles here. We know that Ising anyons, they give you protected Clifford gates, but we need to supplement additional pi/8 gate, which is non-universal, and in order to have universal quantum computation. So the beauty of this idea is that you have these qubits, blocks, and they are protected from quasi-particle poisoning, or so extra electrons that can come and poison fermion and flip fermion parity. So charging energy helps. And also we have electrostatic control of Majorana couplings, which can be done very fast. Certainly microsecond, nanosecond scales. So that's basic idea. This is how these nanowire networks can be grown. So these are indium arsenide selected area grown nanowires, and by properly tiling them, putting proper gates on top of these wires and superconductors, we can control and implement these ideas. So that brings me to the end of my talk, and I just wanted to basically summarize the presentation, my presentation. So I took you on a journey from sort of early years where people were basically discovering anyons and discovering topological phases of matter. So these are 80s to 97. Then there was an idea of topological quantum computation, which was introduced by Alexei Kitaev, and then later developed by people at Station Q, Mike, Chet, and Parsa. It was a culmination of introducing first topological qubit. And then I discussed these practical proposals for realizing these abstract ideas in the laboratory, which started from the work of Fu and Kane on topological insulators and superconductors. And right now we are in this active experimental search for Majoranas, and that era started by the paper from Delft, led by Lutchyn and collaborators. And finally, for the most of my talk, I talked about the simple system, semiconductor, superconductor Majorana platform, which involves garden variety, superconductor, semiconductor, and magnetic field. But if you combine these ingredients in the right proportions, we can get very far, all the way to topological qubit, and probe some of the properties of these Majoranas. And we have concrete ideas how to probe nonabelian, braiding statistics, and quantum computation. So with this, I will stop and thank all my collaborators over the years. And thank you for the attention.
Thanks, Roman, for a beautiful talk. Question?
Roman, this is really in other words, if you measure the parity as you said in the quantum dot, would that not be valuable information stored in my mind?
So this is a difference. Yeah. So the question was, during the measurement process where we couple quantum dot to this Majorana island, why don't I destroy information that was encoded in the qubit? That was the question. And to answer this question, you have to realize that there is a difference between conventional quantum computing and this topological quantum computing, which I alluded to in the beginning, that we don't invoke excited states, right? So we want to project the system to one of the degenerate ground states. Of course, decoherence helps you to do that. So in this case, noise operations, as long as noise does not excite the system, to above the ground state, which would be exponentially suppressed by temperature, and pure dephasing actually helps to project the system to the ground state. So that's the advantage of TQC versus conventional quantum computing, that we need to care only about certain type of errors, where we flip Majorana parity, right? These type of errors. But pure dephasing that does not necessarily do that. So it actually projects the subspace that we want and helps in some sense.
So Noah Bray Ali on Zoom has a question.
Okay.
Roman, great talk. The question is, can you hear me?
Yes, I can hear you.
Great talk. So the question is about this flipping of the parity and about the time scale for 2-qubit operation like the anyon braiding you showed, and in particular how to relate them. So I wonder if you could estimate how many of these braiding operations can I do before by chance I flip the parity? What's the quality factor you think for the architecture that you're outlining?
Yeah, so it's a great question. The quasi-particle poisoning or parity, maybe I should repeat the question or everyone heard. Yeah, so the question was about the fact of parity flipping processes and what kind of fidelity, qubit fidelities do we expect to have, and how many useful operations we can do. Is that fair summary? No?
Well, I'm wondering if you could give us a number.
Yeah, so the numbers are quoted in one of the papers. I can share this paper in the chat and you can look. We've estimated these numbers. But I want to just emphasize that quasi-particle poisoning is device specific. Quasi-particle poisoning rate is device specific. It really depends how well we shield the qubit from electromagnetic radiation, how well we thermalize the system. And it depends on other extraneous factors that are not related to, essentially band structure or something that I know of from calculations. Nevertheless, we use numbers available for superconducting qubits. So it's the best proxy number, and we've estimated these effects. And you can see, you know, I can share a paper on this topic. You can see all the assumptions that we made. But essentially, we find that if the wires are long enough, then these topological qubits, they have very long decoherence times.
Any questions in the room?
Kind of super naive. So you had a slide that showed a scalable design. So can I just go home and build a CNOT gate and demonstrate, or what is it that would prevent me from doing that?
So yeah, so the question from the audience was that I showed simple scalable design. So what is the main obstacle on the way to build a scalable computer and just go home and you know, go home, which contains the illusion fridge, I assume, and measure basically braiding operations and things like that. So the answer to that question, so one of the main obstacles in this field is to make sure that the levels of disorder that we're dealing with are below a certain threshold. That's the main obstacle. This is, you know, material science problem. You know, material science problems difficult to solve, and we know exactly where we want to be. It's just a matter of improving materials, improving fabrication.
Okay, Boris has a question on Zoom.
Yes, yes. Do you hear me?
Yes, Boris, hi.
Yeah, hi. My question is related to previous your answer. I think it is a very long way in material science to go there. In a recent paper, Das Sarma showed that we need concentration like 10 to 15 per cubic centimeter of Coulomb impurities. Practically in current wires, I believe concentration is 10 to 17, 2 orders of magnitude larger. Usually people say 10 to 16, but they forget that these samples of indium arsenide and indium stibum are mostly compensated, strongly compensated. And so 2 orders of magnitude in changing of concentration of impurities, Coulomb impurities, is a long, long way. What do you think?
Yeah, so Boris, let me summarize the question. Boris is skeptical that one can overcome 2 orders of magnitude and lower concentration of impurities in current devices. He is asking, what do I think? Well, Boris, I'm less skeptical than you. And the reason for that, it really depends where these impurities are coming from. In most of the devices, I believe they're coming from fabrication, meaning that, you know, when we deposit gates, we introduce these charge impurities. And so by improving this fabrication, I think we can improve the and lower the density of these charge impurities. And, you know, material science, if you start with fractional quantum Hall, if you go back to quantum Hall effect and you know, look at mobilities and improvement in mobilities in, you know, gallium arsenide, I mean, we've been able to overcome many orders of magnitude there. So why not in these devices? So it is really a material question, material science question. But I think my answer is that, you know, it is a challenge, but I don't think it's impossible.
Okay, so one question in the room.
Could you talk a bit about the algorithm side and what it'll be used for and so on? The last time I heard a talk on that, it sounded like it was really going to be pretty specialized. But of course, that specialization can be powerful. So maybe that accounts for everything. But will it be applicable to scientific computing and things?
Yeah, so the question from the audience, and I think this is a general question for quantum computing.
Right.
So what are the quantum computers are good for? And, you know, if you go back to this early slides that they showed, which sort of highlighted the interest of industry for different applications, that was indication that there is a vibrant community and people are, really trying to exploit what are quantum computers, maybe even small quantum computers are useful for. My personal belief that we have the biggest advantage for simulating quantum systems. So quantum simulations, quantum chemistry, catalysis, that's where I think there is the biggest advantage. Of course, there are other applications which we know, RSA encryption, so basically Shor algorithm, some searching database optimization problems and others. But I think, we need really either large polynomial speed up in order to really embrace the advantage of quantum computers, or use more simulations where we uncover ground state or certain excited states of the system, so these are the two applications that I would highlight.
Will we be able to solve QCD?
I don't know, honestly, but there are ideas in the field.
All right, so there are a few more questions in the chat, but in view of the time, maybe afterwards you can address those. So let's thank Roman again for a wonderful talk.
Thank you.
Next week we'll have Mike Friedman, same time, same place. Thanks, Roman. You see the questions?
I did not see the question.
No, I know you didn't see them before. I don't know if you.
Yeah, I will. Yeah.
Yes, in these days, your time's not over when you're done.
Yeah, exactly.
You have to answer all the questions.
So Mike, how do you think for the next slide is how that'll work?
I was just thinking because
Well, probably better make sure it doesn't. He's at the front. They're just asking.
yes.